black holes are not what we thought. In October 2025, 3 scientists won the Nobel Prize in Physics, and what they discovered changes the most certain rule about black holes, a rule that Stephen Hawking spent his entire career trying to challenge, a rule so precise that for 50 years, not one observation contradicted it, not one experiment challenged it, not one crack ever appeared. When you drift through the emptiness of space, there's a boundary where everything changes, a boundary where you realize that if you do not turn back right now, this will be the end of everything you have ever known. But does it really? There are many things scientists are uncertain of while looking at the rules of the cosmos, yet on this one thing, nobody disagreed. Nothing escapes a black hole. To understand why that's so disturbing, you first need to understand what makes a black hole feel absolutely hopeless. It's merciless. Whatever falls into a black hole will never, ever, under any circumstances, return. We're used to impossible often meaning merely not possible yet. But with a black hole, that's not the case. As you approach a black hole, as long as you remain outside the event horizon, you still have options. You can continue falling in, you can change your trajectory, and you can fire your engines at full power and fly away. But the closer you get to the black hole, the more the geometry of those possibilities itself begins to change. Imagine a river flowing toward a waterfall. Far from the edge, you can row wherever you want, toward the shore, upstream, across the current. Closer to the cliff, the current grows stronger, and you have fewer options. You can still fight it, still choose the right angle, still perhaps break free, but eventually the water carries you faster than you can row. The shore is still there, but there's no way you can get to it. Something similar happens at the event horizon, except instead of water, it's space-time itself. It's structured in such a way that all possible paths begin to lead inward, and the paths outward become fewer and fewer. At the event horizon, the last of them disappears. But beyond that point, even the waterfall analogy breaks down. Movement towards the center ceases to be a direction one can choose or not. It becomes part of the future of any object that happens to be inside. Think about that again carefully. The trajectory toward the center of the black hole becomes, in the literal sense, not metaphorically, part of the future of the poor thing that fell in. It's like tomorrow. You can plan for it in various ways. It may be sunny or cloudy, but it will definitely come. You cannot travel somewhere where tomorrow does not come. The very idea sounds absurd. That's why a black hole is the most reliable trap in the universe. And after all of this, physics makes a move that sounds almost like a betrayal of its own logic. Black holes evaporate. Wait, what? Against the backdrop of everything we know about black holes, this idea does not merely sound absurd, it sounds like a joke. But quantum mechanics has always had a complicated relationship with common sense. 100 years ago, it already forced physicists to make peace with the impossible. And to understand how black hole evaporation can even be a serious idea, we need to look at one of the strangest tricks in quantum mechanics, a trick that lets particles cross barriers they have no right to cross. There is a rule that feels so obvious we barely even need to say it out loud. If you don't have enough energy to overcome a barrier, you don't overcome it. A ball will not roll over a hill if you do not push it hard enough. It will climb to some point, stop, and roll back down. It does not depend on the angle or the material or how long you stare at it. It's simple. Not enough energy means no way through. This rule works everywhere. In mechanics, in chemistry, and thermodynamics. It is so fundamental that we do not experience it as a law, but as reality itself. Quantum mechanics disagrees. A quantum particle is not a ball. It does not have one precise point in space where it simply is. Instead, it has something more like a blurred cloud of probabilities, a region where the particle might be found. And here is the crucial part. That cloud does not stop sharply at the edge of a barrier. It leaks inside. It fades, yes, quickly, yes, but it does not drop all the way to zero. And that means that on the other side of the barrier, the probability of finding the particle is not zero either. It is small, sometimes vanishingly small, but it exists. This is quantum tunneling. It's easy to dismiss this as a theoretical oddity, quantum weirdness, interesting on paper but irrelevant to the real world. That would be a mistake. Tunneling is not something theoretical curiosity buried in equations. It's one of the mechanisms of the world literally depends on. The sun, every second, nuclear fusion takes place at its core. Protons collide and fuse, releasing energy. But there's a problem. The temperature at the sun's core is about 15 million degrees. That sounds like a lot. In reality, it's roughly 1,000 times lower than what classical fusion would require. At that temperature, protons simply do not have enough energy to overcome their electromagnetic repulsion. By the laws of classical physics, the sun should not burn. It burns because protons tunnel through the repulsive barrier. Not all of them and not every time, but often enough to sustain the reaction for billions of years. Every photon reaching Earth right now owes its existence to quantum tunneling. That's literally how a star works. Or take an example much closer to home, the scanning tunneling microscope. This is an instrument that allows us to see individual atoms, not metaphorically, but literally. It works precisely because of tunneling current. Electrons cross the gap between a sharp tip and a surface, even though classically they should not be able to. By measuring that current, scientists can map a surface at atomic resolution. And then there are processors. As transistors in microchips become small enough, engineers ran into a new problem. Electrons began tunneling into places where they're not supposed to go. Not because something was broken, but because the barriers had become so thin that the quantum nature of electrons could no longer be ignored. Tunneling became one of the real physical limits on chip miniaturization. It is not a theoretical curiosity. It is working physics, measured, engineered, used every day. And now we return to the horizon. Near the event horizon, quantum fields do not disappear. In space, there is quantum just as it is everywhere else, and a quantum object near the horizon finds itself in a situation very much like a particle at a barrier on one side, a classically forbidden region on the other, the open space outside. In the tunneling interpretation of black hole evaporation, this is exactly what happens. A quantum particle near the horizon has a non-zero probability of ending up outside, in a place where, classically, it should not be. The most absolute barrier in the universe has just become a probability problem. And in 2025, that probability reached much farther than anyone expected. The Nobel Prize was awarded to John Clark, Michel Deverett, and John Martinez for the discovery of macroscopic quantum tunneling. In plain language, they showed that quantum tunneling is not limited to individual particles. An entire collective quantum system can pass from one state to another through a barrier it classically should not cross. No external push, no added energy, just a probability that refuses to be zero. Previously, this was thought to apply only to elementary particles in the quantum world with its quantum laws. No one could have imagined that something, in the words of the Nobel Committee's own press release, big enough to be held in the hand, could perform the same kind of miracle. All of this forces us to look again at the most impassable barrier in the universe. Maybe there's a way back out of a black hole after all. That question would be easy to dismiss, if not for the man who first dared to suggest that black holes could radiate at all, Stephen Hawking. And he did much more than that, but not right away. In 1971, he proved a theorem. Truly proved it, mathematically rigorously, within the framework of general relativity. The theorem stated that the surface area of a black hole's event horizon can never decrease, never, under any conditions, through no external or internal process. If two black holes merge, the total horizon area only grows. If a black hole absorbs matter, the horizon expands. It cannot shrink. This wasn't merely a technicality. It was one of the fundamental findings about the nature of black holes. They could only grow. 3 years passed, and in 1974, the same Hawking published a paper implying that black holes slowly lose mass, that the horizon shrinks over time, that eventually the black hole disappears entirely. He had disproved his own theorem. To understand how this was even possible, we need to step back a little to what Hawking was working on in the early 1970s. At the time, black holes belonged almost entirely to general relativity. Quantum mechanics had already shown that reality could violate common sense, but few physicists were eager to bring that logic to the event horizon. Hawking focused on exactly that. In 1973, he visited Moscow, where Soviet physicists Yakov Zeldovich and Alexei Starobinsky showed him that, according to the principles of quantum mechanics, rotating black holes should create and emit particles. Hawking was skeptical, but the idea stayed with him. After returning home, he began calculating on his own. The calculation took several months, and when the result emerged, Hawking himself was reportedly surprised by it, and not pleased, because the equations implied something that should not have been possible. The event horizon is not silent. Radiation must be coming from the vicinity of the black hole. Thermal continuous radiation, even if unimaginably weak, but real. It turned out black holes were not entirely black after all, in every sense of the word. For several weeks, the scientist searched for an error in his own calculations. There was none. The paper was published in March 1974 in the journal Nature. Brief, almost without details, under a title ending with a question mark: Black hole explosions? The reaction from the physics community was, to put it mildly, cautious. The discovery that black holes radiate came as a complete shock to the scientific world, since until then it had been believed that nothing, not even light, could escape a black hole. Hawking's academic advisor, Dennis Sciama, later called the discovery brilliant. John Archibald Wheeler, one of the greatest physicists of the 20th century, said that even discussing Hawking radiation gave him physical pleasure. But at first, there were also those who believed the result must be a mistake. Then other physicists double-checked the calculations and confirmed them. But how does it work? That's the main question. The event horizon we just discussed, the place where the outward trajectory vanishes, does not go away. The geometry doesn't change. Still, nothing emerges from beyond the horizon. So where does the radiation come from? Hawking found the answer in a place where classical physics would never have thought to look: in the quantum nature of space itself, right at the horizon. Among all the strange wonders of quantum theory, one matters here more than the rest. Empty space is not really empty. At microscopic scales, quantum fields are constantly fluctuating. In popular explanations, this is often described as particle-antiparticle pairs appearing out of the vacuum. They exist for a fleeting moment, almost immediately annihilate, and disappear again without leaving any visible trace. In ordinary space, this doesn't produce any real radiation. The pair appears, then disappears. The balance is preserved, but near the event horizon, things are different. Imagine one of these pairs appearing right at the edge of a black hole. One particle ends up outside, while the other slips beyond the horizon. The one outside can escape into space. The one inside can never return. To an outside observer, it looks as if the black hole has emitted a particle. But this is where we have to be careful. That particle did not fly out from deep inside the black hole. It's not carrying a message from beyond the horizon. It has not violated the rule we just established. The event horizon is still a boundary from beyond which nothing returns. The radiation does not come from inside the black hole. It emerges from the quantum region right at the horizon. But that raises the next question. If the escaping particle carries positive energy away, where did that energy come from? The answer sounds strange, but it's exactly what makes the process physically consistent. The second quantum, the one falling inward, can be described as carrying negative energy relative to an outside observer. So the balance is preserved. A particle with positive energy appears outside, while the black hole's mass decreases by the corresponding amount. So Hawking radiation does not mean that a black hole has sprung a leak and started releasing its contents back out. What happens at the very edge is a quantum process that gradually drains the black hole's energy from the perspective of the outside world. The particle pair picture is useful and intuitive, which is why it's used so often. But it should not be taken too literally, as if a tiny particle generator were constantly clicking away at the horizon. Hawking's actual calculation is subtler than that. It deals with quantum fields in curved space-time. And later, the tunneling interpretation of black hole radiation emerged, bringing us right up to the most dangerous question of all. Could something, after all, escape a black hole. This is the point where the beautiful version of the story can mislead us. Macroscopic tunneling does not mean that something which once fell into a black hole can now jump back out. A rock, a cloud of hydrogen, or a piece of a star. In the Nobel Prize experiments, it was not an object tunneling like a tiny ball through a wall. What tunneled was the state of a system, a collective quantum variable in a superconducting circuit. In other words, physicists did not show that a large object can simply be dragged through a forbidden region whole. They showed something else, that quantum rules can govern systems that can no longer be described as just a single particle. And for black holes, that's not a rescue hatch. Anything that has once crossed the horizon still does not return to the outside. The event horizon does not become a leaky wall. No debris flies out of it, no signals, no records, no traces of dead stars. Hawking radiation arises right at the boundary, and it does not look like the contents of a black hole escaping back out. It looks like new, almost random thermal noise. And that is much worse, because the black hole still loses mass. It shrinks, it evaporates. In the end, it disappears. But if what fell in never comes back out, if no particles, no signals, no imprints of the past return, then a question appears that physics can no longer simply wave away. Where does the information go? Information? What information? And this is where one of the most tangled paradoxes in modern physics begins. Imagine two identical black holes. Into one of them, we throw an encyclopedia. Pages, ink, letters, diagrams, every sentence ever printed inside it. Into the other, we throw a plain cloud of hydrogen. No structure, no text, no hidden meaning, just the simplest atoms in the universe. These are not the same things, not even close. One carries an enormous amount of structure. The other is almost featureless by comparison. But after enough time, both black holes evaporate. And according to Hawking's calculation, what comes out looks the same. Thermal radiation, almost random noise. From the outside, the black hole doesn't seem to remember whether it swallowed an encyclopedia or hydrogen. That is where everything breaks down, because physics says those two histories cannot simply be identical. To see why, we need to be precise about information. When physicists say information, they don't mean texts or files. They mean the exact configuration of a system. Take a simple object, a cup. It's made of atoms. Each atom has a position, a velocity, an energy. All of that together is a specific configuration. That's information. Now imagine the cup falls and breaks. If it splits into a few large pieces, you can put it back together. The shape is damaged, but not irreversibly. If it falls from a height and shatters into dozens of small fragments, reassembling it is harder, but nothing fundamentally changes. It's still possible in principle. No matter how hard you smash the cup, no matter how many pieces it breaks into, nothing fundamentally changes in terms of information, even if you blow it up. The fragments scatter, some energy goes into heat, into sound, into vibrations in the air. A second later, what you have is not a cup, but chaos, shards, dust, warm air. As far as we can tell, the cup is gone. But on the level of physics, nothing has disappeared. All the atoms are still there. They've just changed their positions and velocities. If you could freeze that moment completely, capture the position and motion of every atom, every photon, every air molecule, you could run the process in reverse and reassemble the cup from that chaos. Not because we know how to do that from such a hopeless state. We don't. But because it's possible in principle, because the original state is still encoded in the current state of the system. This applies to everything at any scale. You can burn a book. You can destroy a mountain. You can scatter a planet into a cloud of plasma each time the structure is destroyed. But the information doesn't disappear. It just spreads across an increasingly complex system. This reflects one of the core ideas of quantum mechanics. Any transformation of a system is reversible in principle. If you know the exact final configuration, you can recover the initial one. Information can dissolve into an enormous number of interactions, but it doesn't vanish. That is why the black hole is such a problem. Quantum mechanics says information cannot simply vanish without a trace, but a black hole, apparently, does exactly that. This is the information loss paradox. When matter falls into a black hole, it carries information with it, a specific configuration. Which particles with which spins, energies, and entanglements. It's not just matter. It is a precise physical history. But Hawking radiation is thermal, and it does not carry information about what exactly produced it. A simple example. If you heat a piece of iron, it begins to glow. From that glow, you can determine its temperature, but you cannot reconstruct what heated it: a gas burner, a laser, or an explosion. The same thing happens with a black hole. It radiates as if only its mass matters, not what once fell into it. When the black hole evaporates completely, nothing remains. No black hole, no information. A broken cup can, in principle, be reconstructed. But if that cup falls into a black hole, and the black hole later evaporates, then, according to Hawking, the information about the cup is destroyed forever. And this is where the two theories stop agreeing. Quantum mechanics says information is always preserved. From the final state, you should always be able to reconstruct the initial one. But general relativity, combined with Hawking radiation, seems to say the opposite. A black hole can destroy information. Both theories work. Both have been tested with extraordinary precision. But here, they cannot both be right. If information cannot be destroyed, then the black hole has left physics with only one possibility. The information must still be somewhere. But where?